Hey, Algebros. You guys have been through the ringer recently with a whole lot of systems of equations, solving and solving and solving, and I applaud you so much for getting this far, and in one piece, too. While this is my favorite unit in algebra, I also acknowledge that it's tricky, especially when you have processes like these that have so many steps to them. However, going forward, now that we're done really testing you on each of those methods, I'll mostly allow you to pick between substitution and elimination and see which one works better for you. Because at the end of the day, if one really clicks with you more, I'm not going to stop you from using that method and really just running with it. So here, I want to talk about a special kind of, well, kind of more so two special kinds of systems of equations. I'm going to call this lesson the oddballs. So when you see the word oddballs, you mainly think about ones that are different from the pack. Different from the pack. And it's not like they look different or they're mangled or deformed or anything like that. It's just that their solutions end up doing something really weird. But at the end of the day, that weirdness is not exactly something we haven't seen before. I'm going to give two examples real quick. The first example of oddballs is as follows. And we'll give it a name later. So let's leave the name blank for right now. Let's take the example of the system of equations y equals, 12x minus 1. And the second one being y equals 12x plus 11. Equation 1, equation 2. The instructions here are going to be to solve this kind of equation. All right? If we want to find the easiest way to do this, we note that both equations are already in the form of y equals. So I'm going to use the substitution. So since we have y equals in both cases, let's use substitution. So here, I'm going to set them both equal to each other. 12x minus 1 equals 12x minus 11, or plus 11. I'm going to work around with those constants and make sure that we have them on the right side. We'll have 12x equals 12x plus 12. A lot of 12 here, and you might already see something fishy. But we're about to truly see something fishy when I get all the 12x's on one side. 12x minus 12x ends up 0. Oh no, the world exploded, run! No, don't really run. It's all good. And I hope I didn't blow anyone's ears out if you're listening to this on headphones. But anyway, we've encountered an impossible situation. Again, 12 can't equal 0. Remember what we said about impossible situations when we get to something like this. This is a situation when we would have no real solutions. And if we were to solve this graphically, I'd get two parallel lines. So this is a situation where a system of linear equations can have no real solutions. So our first oddball, if you go back to that gap we left, is no real solutions, and that's a situation where you get something impossible. When you get something impossible. This isn't something that's brand new. We've already seen this when we talked about colliding equations, but now we're applying it full-time to this. All right. I could show you this in GeoGebra just to show you for sure that this is exactly what we're dealing with. So in that case, one of the equations is y, equals 12x. That's not an x. 12x minus 1, I believe I set that one to be. And the other one is y equals 12x plus 11. If I'm off by a little bit, it's still the same concept. Once again, go on and on forever. These lines will never meet. There's no intersection point, so therefore there's no solution. And again, it's no big deal that you don't have to copy that down. That graph showing right there was just for demonstration. All right? It's just to show that there is no real solution in this case. All right? So there was that one. The second oddball, I will once again leave the title empty for you, and I'm going to give you an example of a problem in just a moment. Let's see the example that demonstrates this as 3x plus 2y equals 10. And 9x plus 6y equals 30. All right. This is once again a system of linear equations. Call them 1 and 2. This case, let me use elimination because we have no easy coefficients to work with. No easy coefficients. But I do see an elimination shortcut. Take a look at our x's or our y's in this case. In either which case, we notice that 3 times 3 gives us 9, the other coefficient. Or in the case right here, 2 times 3 equals 6. In other words, the other coefficient. The 6 down here, the 9 down here. So in this case, it's more so a situation of I just need to multiply one equation by a certain number. So here I'm going to make that be 1. First of all, I have to multiply by 3 necessarily in order to cancel out our 9. I'm going for canceling the x's. So let's see if we cancel the x's. It's the same method for the 9s, though. For not the 9s, the y's. So if I multiply it by 3, equation 1 will become 9x plus 6y equals 30. The other one will be 9x plus 6y equals 30. So you notice something funky already. But let's address it in a moment, because right now we can't cancel anything out. So that's why we don't just cancel out by to multiply equation 1 by 30. I have to multiply it by -3. Therefore, all the signs have to reverse. Now I'm able to add. But notice what happens with every single term. You probably already noticed before that we have the exact same equation twice. And that's by design. Because when you add everything together here, you will get 0 over 0. The magic goggles. Magic goggles that are always true. So remember, if we ever got a situation like this when we were dealing with colliding equations, we said that this had infinitely many solutions. Maybe you were already able to deduce what the second oddball was by that, but that's our second title right here. Infinitely many solutions. This is the one where we get something that's always true. Or in other words, the 0 equals 0. All right. Again, when it comes to these methods, you can use substitution or elimination, whichever one is easier for you. And that's what I want you to do for the you try for next time. Yeah, this one was way shorter than the other 2 lessons, I'll say that. So the you try this time. Solve each system using the algebraic method. Of your choosing. Speaking of which, I just want to mention right here, recall, when you have infinitely many solutions, remember that means that the lines overlap. Just as a quick little recall there. I forgot to mention it. So anyway, for this case right here, I'm going to give you 2 systems, 1 and 2. The first system is going to look as such. 3x plus 5y equals 10, and negative 6x minus 10y equals negative 20, equations 1 and 2. I'm not going to use ones and stuff with circles. I'm just going to have number 1 like this, and number 2 like this in order to better differentiate them. And the other system, I want it to be as follows. I want it to be 7x minus y equals 3, and then 21x minus 3y equals 1. Equation 1, equation 2. Have fun with these algebros. We're almost at the finish line for the Systems of Equations unit. We have 1 lesson after this, and then we'll be right as rain. I'll see you then.